All right, we're back with deal 2 in Math 676, and what I would like to talk about now is the Step 2 tutorial program. So Step 2 is we talked in Step 1 about the mesh, and if you remember the lecture where I walked you through the various different parts of let's say the mathematical description of a finite element program, the mesh was always the first one. The second one was that we need to talk about degrees of freedom, namely, let's say, where are shape functions located on the finite element mesh. And Step 2 is the first one that deals with this question, let's say, what is the finite element and where are shape functions on the reference element? So, for example, for a Q1 element, for the bilinear element in 2D, shape functions are located on the vertices of the reference cell, and then consequently they're also located on the vertices of the mesh. And so what I would like to talk to you about is a little bit about what this means for the overall mesh and what that means for the resulting matrices that come out of this. So Step 2 shows essentially how you associate degrees of freedom from a finite element to a mesh. This is done by a class that is called DOF handler, DOF for degrees of freedom. And then the key part that relates to this is how degrees of freedoms are connected by the bilinear form, that is the, for example, grad phi I, grad phi j form for the Laplace equation, what that means for the matrix that comes out of this. Now, for all finite element programs, the system matrices that we get out of this are always sparse. Sparse means that there is a relatively small number of non-zero entries per row in this matrix. So, for example, you've seen this in the simplest discretization of the Laplace equation, which would be, for example, the 5-point stencil that comes out of finite differences. You've seen that there's exactly 5 entries for every row in the matrix, at least for those rows that correspond to interior degrees of freedom. The same is true for finite elements, that there's always a relatively small number of entries per row, and that the number of entries per row is not dependent on the overall number of degrees of freedom. So if you have a 10 by 10 mesh, you have 5 entries per row. But if you have a 1,000,000 by 1,000,000 mesh with 10 to the 12 unknowns, you would still have only 5 entries per row. So that's what we call a sparse matrix, where the number of entries per row in this matrix, let's say the number of non-zero entries per row of this matrix, is independent of the total size of this matrix. So for PDEs, for the finite element method, the system matrices are always sparse. And that is a result of the fact that we define shape functions locally. We define them, for example, on every vertex, and they're non-zero only in the cells around this one vertex. That is the one factor. The other factor is that differential operators are local. That means that let's say that they are not coupling the value of a shape function here to the value of a shape function somewhere else. So that is a difference between local differential operators and integral operators, for example. Integral operators, let's say, have the form integral, let's say, phi I of x times phi j of y times k of x and y dx. And that would couple phi I at x with phi y at j. Differential operators don't do this. They evaluate shape functions, all of the shape functions in the integral, at exactly the same location, at x. And that means that if phi I is 0 at this particular x, then the corresponding matrix entry aij is 0. Both of these shape functions have to be non-zero, or the derivatives have to be non-zero at a particular location on one cell for the corresponding matrix entry to be non-zero. So this results in a sparse matrix. And the sparsity of matrices in the finite element method is something that is not a coincidence. That is something that is absolutely crucial. You cannot overestimate the effect of sparsity to the success of the finite element method. When you go back in the history, for example, the idea of something like the Galerkin method that we talked about in one of the previous lectures, where you just have shape function, or where you just have trial functions phi I and phi j, for example. back in the day, let's say in the 1920s, 30s, 40s, when these sort of methods first came up, people used all sorts of functions. For example, phi I could be sine I times x, and phi j could be sine j times x. These are not local functions, and as a consequence, the system matrix that you get out of this would be a full matrix. And at the time, people didn't care so much because their matrices were 5 by 5 or 7 by 7. It didn't matter whether the matrix is full or sparse. But today, of course, we can solve problems that are much bigger, where we have thousands, tens of thousands, up to billions of shape functions, and it makes a huge difference if the matrix is sparse or if it is not. In particular, it's very easy to see that you cannot store a million by a million full matrix where every entry is non-zero. We can only store big matrices if they're sparse. And so the fact that finite element matrices are sparse is a crucial factor to the success of the finite element method. We could not use the finite element method if the matrices were not sparse. So let me give you a little example. I'll come back. So I have, again, this figure that I used in one of the previous lectures that shows a triangular mesh, even though in deal.II we cannot deal with triangular meshes. But the idea, of course, is exactly the same whether your mesh is triangular or quadrilateral. So let's say in this particular mesh here, I have enumerated my degrees of freedom as follows. So I call this degree of freedom, so the shape function that is associated with this vertex here 0, and this 1, and this 2, and so on and so forth. And let's say I want to solve the Laplace equation. So the entries of my matrix are aij equals the integral grad phi I times grad phi j dx. So if you look at this, of course, so the shape function that is located at vertex 0, you have seen that how they are defined. They are, the shape function 0 is 1 at this vertex, and it is 0 at all of the other vertices. So it decays from 1 to 0 along this edge, and along this edge, and along this edge. And shape function 0 is 0 in all of these cells over here. So if I look at the entry a00, that would mean that I need to integrate the gradient of phi 0 times the gradient of phi 0. Well, that is a non-zero function. In particular, it's the non-zero value. The same is true for the integrand where I multiply grad phi 0 with grad phi 1. So that too would be a non-zero value. And for the matrix entry A02, and for the entry A06, for example. Whereas the entry A03 in this matrix is going to be 0, because the shape function 0 only lives on these two cells here, whereas the shape function number 3 lives on these 3 cells here. So if I look at the integral here, the integral over omega, I can write this as a sum of the integrals over the individual cells. If I look at every single cell that I could possibly integrate over, either the first factor is 0, or the second factor is 0 when I integrate gradient phi 0 against gradient phi 3. So one of these two factors is always 0, and as a consequence, the entire term A03 is 0. So if you look through this entire mesh that we have here, it turns out that for the row number 0 in this matrix, there are exactly 0, 1, 2, 3, 4 entries, of course, that are 0, whereas the other 1, 2, 3, 4, 5 entries are 0. And you can easily understand that if I make this mesh finer and finer, for example, if I added cells over to the right, or if I subdivided each cell into 3 child cells or 4 child cells, for example, that the number of non-zero entries in this matrix will stay relatively constant, because it is always just those cells where shape function 0 and the shape functions from associated with the same cells that shape function 0 is on are non-zero. Whereas all of the other cells that I add to my mesh, they will all produce 0 entries in this matrix. So the sparsity is always in such a way that the number of non-zero entries is essentially given by the number of neighbors each vertex has in this mesh. And the number of neighbors each vertex has in this mesh does not depend on how big this mesh is, how many cells it has. It only depends on, let's say, the local neighborhood of a particular vertex. So the bigger the mesh, the more zeros there are per row, but not the more non-zeros. That's the hallmark of sparsity. Now, the other thing that I would like to point out is that, of course, I can renumber degrees of freedom. So, for example, I showed you a mesh where I called this vertex here number 0, and this number 1, and this number 2, and this number 3. But I could, of course, have enumerated them in any other way as well. I could have called the one over here 0, and this one 1, and this one 2, and this one 3. In the end, how I call these vertices is arbitrary. This is a choice that I can make. And of course, if you think about what that means, ultimately the solution that I will get from the finite element method will be exactly the same, right? The solution of the finite element method does not depend on how I enumerate these degrees of freedom. Of course, how I enumerate the degrees of freedom makes a big difference what I mean when I say, for example, the first component of the solution vector, u. So if I look at u1, what does that correspond to? Well, let's say u1 is not the first, but the second component if I start counting from 0. So u1 in the left mesh would be the value of my solution at this point. Whereas if I had enumerated my degrees of freedom like this, then u1 would be the value of the solution at this particular point. So you see the difference in the interpretation, but the solution is going to be the same. The solution vector is different, but the solution as a function uh of x is the same. So I can re-enumerate degrees of freedom, and if you think about it a little bit, you will find that this is, of course, just a permutation of the degrees of freedom. And as a consequence, what that means is if I re-enumerate degrees of freedom in a different way, then that means that I permute the elements of my solution vector, I correspondingly permute the elements of my right-hand side vector, and I permute the elements, the rows and the columns of the matrix. But other than that, everything stays the same. In particular, all of the properties of the matrix, like the condition number and so on and so forth, the norm, they all stay exactly the same. So what I would like to talk about in step 2 is how you represent this in code. So if you go to the page where we have the documentation of step 2, so I give you this link here for an older version of deal.II 7.1, we can do exactly the same kind of steps that we've always done in step 1 or in the previous lecture for step 46. So you go into this directory, you call cmake with the directory into which you install deal.II, and then you call make run. It will produce output that shows you the what step 2 actually did. And so let me do this real quick here. So let me let Eclipse disappear. So I'm going into step 2. I call cmake with the path to deal.II. I call make run. It's going to compile step 2, and then it's going to execute it. And what I end up with is our two files, sparsity pattern 1 and sparsity pattern 2. And I'm going to show you what these do, or what they look like. But let us first go through this through the code, and I'll walk you through a little bit what it actually does. So, sorry, not Firefox. I need to go to deal.II.org. I want to go to the documentation of the latest version, which right now is 7.2. I go to the tutorial. I click on step 2. And let me look at this. So this is a typical tutorial program where, again, you have an introduction that gives you a little bit of an overview of what is happening here. You have the commented program. There is some so there's a lot of documentation. Again, there's some output here. And then you have the plain program where I have stripped all of the comments out. So let me walk you through this program a little bit. So when you read it again, as always, we start at the bottom and look at what the main function does. So in this case, in the main function, we create an object of type triangulation here. That's, of course, exactly the same as we did in step 1. And then we call a function that is called makeGrid, and as argument, it takes the triangulation. So makeGrid is a function here. And it turns out that makeGrid is exactly the same function as we had in step 1. So it is, in particular, the second grid function of step 1. It produces the concentric shell that is refined towards the inner edge. So you remember the mesh that went along with this. So there's not that much to discuss here. Let me go back to main. So the second part that I need to discuss is we create an object of type DOF handler. As I said, DOF handler is the object that associates degrees of freedom with each of the vertices of the cell, or if you have higher order elements, let's say if you have quadratic elements, it would also associate degrees of freedom with the edges of the cell of the mesh and with the cell interiors. So the DOF handler is the instance that enumerates all of the degrees of freedom in this mesh wherever they might be located. And it needs to know about the mesh, of course, so it takes the triangulation as an argument. And then we call a function called distribute DOFs here. So let us look at this one here. So distribute DOFs is this function here. Like I say, it takes the DOF handler as an argument by reference. And then we create a finite element. So we want to use with the usual Lagrangian interpolation elements, and they're called FEQ. So that's we call the elements on triangles the P elements. So P1 would be the linear elements on a triangle. Q1 are bilinear elements on a quadrilateral. So our class is called FEQ. We still work in 2D, so it still has the argument in angle brackets 2 here. And the constructor argument, so if you want to, you can click on FEQ and you will come out at the documentation of this FEQ class. The documentation will say that the argument to the constructor is the polynomial degree. So in this case, we use 1. That means we use bilinear elements in 2D. If this argument was 2, we would use biquadratic elements. And then we call this DOF handler that already knows about the mesh. We call the DOF handler with this particular finite element. So the function that we call is called distribute DOFs. And what it's going to do is it already knows about the mesh. Now it also knows about the finite element. The finite element can describe how many degrees of freedom it has per vertex, per edge, per cell, and so on and so forth. And it's going to enumerate them all. So it's going to go through this mesh, and for the Q1 element that we have here, it's going to enumerate every single vertex in this mesh. So this is what happens here in this function called distribute DOFs. And then the next thing that I would like to do is, so I don't want to build a Laplace matrix right away. We're going to do this in step 3, where we're going to talk about actually solving a real Laplace problem. So right now, all I want to do is I want to figure out in this matrix that we're going to get on this mesh with this particular finite element, where are the non-zero elements going to be? This is an important step because we have to talk about later when we want to store the matrix, we have to allocate memory for it. So we need to know where the non-zero entries of this problem are going to be. And so the first step is always to figure out where are non-zero entries, and then to allocate memory for the matrix so that we can actually store the values of these non-zero entries. In deal.II, there's a function that is called makeSparsityPattern that builds this sparsity pattern. The sparsity pattern is essentially in the information of where are non-zero entries in this matrix. It turns out that in order to build these sparsity patterns, this is a slightly complicated process because the way we store these matrices is that we'd like to store all of the entries of this matrix in one big array, one after the other. So we start in the first row and we store all the non-zero entries, and then right after this we store all the non-zero entries of the second row and of the third row, and so on and so forth. So in order to do this, we need to have a fairly good estimate, or we need to know where all of these non-zero entries are. But when you build these sort of arrays up front, you don't know how many non-zero entries exist. And so what we typically do, let's say in a naive way, would be we get an estimate of what is the maximum number of non-zero entries per row. And then we would allocate, let's say the upper bound would be at most 10. And so we would allocate 10 entries in the sparsity pattern for every row, where we could store for the first row what are the column numbers of these non-zero entries, and then immediately after that what are the column numbers of the non-zero entries of the second row, then what are the column numbers of the entries in the third row. If our estimate of what the maximum number of non-zero entries is too large, let's say we have estimated 10, but in reality we need only 5, then we need to allocate 5 times as much memory. Then we find out which are the non-zero entries in each row, and we find that, well, we used only 5 out of these 10, and then there's a process where we would compress the sparsity pattern. That works well in 2D, because in 2D we can get reasonable estimates of the maximum number of non-zero entries per row. But in 3D, or in particular for HP finite elements, it turns out to be almost impossible to get a reasonable upper bound. So typically what you have is that there are, let's say, 10 non-zero entries per row, but the upper bound that we can estimate, the best thing that we can do, would be that we allocate 120 entries per row. So you have just overestimated the amount of memory that you need by a factor of 10. And what often happens in these cases is that you allocate 2 gigabytes of memory, and you only need 150 megabytes of memory. Now, 2 gigabytes a day is a size that we can deal with, but if you have a bigger problem, then you allocate 20 gigabytes of memory, even though you really only needed 1.5 gigabytes of memory. And what happens is that because of your bad estimate, you blow your memory budget, and the operating system terminates your program. So what we do in practice is that we first build a temporary sparsity pattern that uses a different memory structure that doesn't require us to come up with an upper estimate first. And so I'd like to show it to you here. So the data structure that we use as this temporary sparsity pattern is a class that is called compressed sparsity pattern. And there's a lot of documentation about all of these sparsity patterns, so if you're more interested in this, click on it or read the introduction of, or the documentation of step 2 in more detail. So this compressed sparsity pattern only needs to know what is the size of the matrix going to be. That is going to be, I can ask the DOF handler for the number of degrees of freedoms, n DOFs. So it's going to be a square matrix. So the compressed sparsity pattern in the beginning doesn't allocate any memory at all. And then I call DOF tools make sparsity pattern with this DOF handler, and it's going to fill the compressed sparsity pattern. And so once we have built this temporary structure, I can build the structure that we use to actually store the elements of this matrix. So the matrix that I'm going to use in step 3 is a class that's called sparse matrix. It builds on an object that is called sparsity pattern, and I can build this sparsity pattern now that I have built this temporary one. So now that I have collected all of the column indices of the non-zero entries for all of the rows of this matrix in this class compressed sparsity pattern, I can copy this from compressed sparsity pattern into the actual sparsity pattern. So this is what happens here. So I allocate a sparsity pattern, I copy the temporary one, and then what I'm going to do is I'm going to output this into a file that I'm going to call sparsity pattern 1. So I'm going to output this in a format that is called GNUplot. GNUplot is one of those rather old and maybe somewhat crafty visualization programs, but that's still very good if you just want to quickly visualize something. So what I'm going to do is I'm going to show you real quick how this goes. So I call GNUplot, and then I'm going to say plot sparsity pattern.1. Actually, I should show you what's in this file first. So the sparsity pattern.1, it lists every non-zero entry in this matrix. So 0, 0 means that the top left entry of the matrix is non-zero. 1, 0 means that the entry at I equals 1, j equals 0 is non-zero, and so on and so forth. So these are all the coordinates of the non-zero entries of this matrix that would correspond to the finite element matrix. And so if I call GNU plot, I can say plot sparsity pattern.1, and it's going to give me a graph like this. So what this shows is that this matrix here is going to be roughly, 1300 by 1300. And you see that on the diagonal there are non-zero entries, and then there's a few out here and a few out here. So what you don't see so well is that each one of these points here is actually multiple entries, and I can do this by saying plot sparsity pattern.1 with dots. So that is going to give me in a picture like this, and you may see that there's a lot more structure here. So it's not just the diagonal, but it is also off the diagonal that there are multiple entries. So what you see here is these are all of the places in this matrix that are going to be non-zero. Whereas all of these other places where everything is white, these are all of the zeros in this matrix that I will never have to store. And as a consequence, I can, of course, get away with a much smaller memory amount than if I stored this matrix as a full matrix. As a matter of fact, even a 1300 by 1300 matrix would imply something like 2 million elements in my matrix. That's already 16 megabytes for such a small problem here. You can easily imagine what that would mean if you had a million by a million matrix and you needed to store every single entry. That's just not feasible. So we really need to use the sparsity that we have here to limit the amount of memory. So this is essentially just the first part of what we can do with step 2. Step 2 has another component where we re-enumerate these degrees of freedom, and you should feel welcome to look this up in the online documentation and to play with it. It is always useful to play with these sort of programs, but I leave this to you. And with this, let me move on from step 2 to step 3, and we'll come back to that in the next lecture.